number is 8, and then we also want to write down the values for the set of quantum numbers n, l, m, okay, and l and ms for each electron. So let's start with this atomic number. Okay, atomic number is 8. Then how many number of electrons do we have? 8. Very good, yeah. So where we have the same number of the electron, yeah, as the atomic number. So we need to find the space to fill these 8 electrons. Alright? So filling those electrons can be done, yeah, using this paper. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. I will stop here because I think these are enough, yeah, to accommodate 8 electrons. So let's first start with this. So we will fill 1s space, and then how many electrons can be accommodated in the s shell? How many electrons can be accommodated in the s shell? Yeah, how many electrons can you put? 2, yeah? Because it's S shell, yeah? 2. Now we will move on to this next solution. So again, this is S, okay? So we are going to put 2, alright? And then the next sequence is following this arrow, so we will fill the 2p shell. So how many electrons can be accommodated in the p shell? So what's the maximum electrons you can put in the p shell?
Yeah, no, it's here. Like this is one shell, I think. So you can
How
put
many
4.
electrons can you put?
P 是 6还是 8 啊 ？Maximum electron
P 啊，应该是4个。
4个。
Well, P means your L is 1, yeah? When you have one of these angular quantum number, then your Mn can have a -1, 0, and then 1. And under each of these magnetic quantum numbers, so you will have 2 spins, yeah? So how many electrons you can accommodate inside the P shell?
会 study 这个。skin 出来的，认识。
6, yeah? 2,
对。
2, 6. So 6. Now, if you add up all those electrons, it becomes, well, 10. Okay? So, we have only 8 electrons, so our last subshell is going to accommodate only 4. Then we have altogether 8. Yeah? Therefore, this quantum state of these electrons is going to be written as 1s2, 2s2, 2p4. Now we have to write out values for the set of quantum numbers, okay, for each electron. So we want to describe each of those electrons, yeah? So let's first start with 1s2, okay, and then I found myself it's convenient to make kind of a table, so I will start with n equals 1. Because the principal quantum number of 1s shell is 1, yeah? Then what is corresponding to this angular momentum quantum number under this 1, and the s subshell, this must be 0, yeah? Because it's s shell, so 0. So what's allowed magnetic quantum number then? When L is 0, the allowed quantum number for ML is 0, yeah? So 0, 2. Then we have 2 spins. 1, 2. Alright. Now let's move on to this 2s2. What's principal quantum number for this shell? 2s2? 2, yeah? So this is 2. Then what's our orbital momentum quantum number? 1. You sure? We considering this as a shell. Therefore,
I think we see next time we right here again.
and then our
So
MS
9:30 again.
will be
This
one.
general section will ship then we come here
Two.
9:30. Makes sense.
Now let's move on to this two people, right? So we will have the same quantum number as 2.
No, but if you
And then what's
if you
our
don't circle,
angular
right,
quantum
then it's not
number?
you. When else before?
For the P shell,
You want?
quantum
You
number
don't
is going to be
circle.
1, yeah? Very good.
Huh?
1.
not even like going to think
Then,
just
what's around
Yeah, why cannot? But I think
magnetic
I
quantum
need to
number under this 1?
If you not saying you say by 15 April. See now.
Very
You
good,
know,
yeah?
you know, fuck it, let's do something.
1,
thinking for
Huh?
0,
okay,
and then 1.
As in,
Okay,
you really
and
don't
then
understand what.
under each of these magnetic quantum numbers, we
Okay,
have
go on.
2 spins, yeah? So this one will have 1 or 2 and then minus 3. Okay,
You and
then
us like different. Like,
we
you know,
already
different
feel
thing.
1, 2, 3, 4, 5, 6 electrons, and then we are left with only 2 electrons.
The email you.
And we have only 2 electrons, but
based
there are
on
4
based on
spaces, 4
Yeah.
vacancies.
You ask for it.
So how
It's
are we
there,
going
there.
to
Huh?
fill?
I need to email them. No, fucking.
So we are going to use,
Like,
we are going to
except
follow
two
this
things.
Kunz rule, yeah,
It's
Kunz
into the
rule.
answer already.
So
She said
Kunz
just
rules
dealing with
states
the
that
organization.
Oh, me, like
when
that.
we fill
No,
this
it's
electron,
whenever
okay, fill
they
this
asked me to do
state with
self-serve. Then I
electrons,
asked them why I need
we
self-serve.
want to
I
make
thought you in place.
maximum
girl asked me to
number
send-
of
Send the
unpaired
photo
electrons.
instead. Because
Okay,
laptop
unpaired
for
electrons. Therefore, I will
You do
just
anything,
put
you do
it as
anything with what?
Just
2
answer me, yeah.
under this
Yeah, that's what
magnetic
I only got
quantum
something
number
else.
and then
Like,
another
yeah,
one
officially,
over 2 under this magnetic quantum
You
number.
do.
Therefore, we have
Straight away.
2
Straight away.
electrons which are
Email
unpaired.
them. The fucking.
Okay, which are unpaired. So we have unpaired quantum numbers. Yeah. And then all those blank boxes, I will just copy the same number. So copy over. Yeah. 1. So now we have these quantum values for each of the electrons.
Like that.
So quantum state is this, and then yeah, we can find all these the quantum values for each of the states, and then in the last
Mine's like that.
stage, we are going to use this Kunz rule, right? We are going to make
100 hours.
maximum number of electrons having
Only work how many
unpaired.
hours?
I don't know.
What's the working day?
Now,
Fine.
I will
What
show
time?
you
They
one
never
of
tell
the
what time
following
start.
questions.
Oh.
Question number 5. The
Nine
atomic
to
number
five.
of rotation is 20, and the
What
write
time?
down the electronic configuration for the ground state
How
of
much are you already?
rotation,
Where that
and
put?
then list the values for the second quantum numbers and
Very
L,
sure,
I can't.
for each
No comments.
electron.
Just hope we
Right,
can
so
keep
let's
going.
try to do this.
I think should have right out of the internet.
Why is it? Engine school.
Science.
Science.
So,
Yeah, why not?
atomic number is
Like, we
given
compare
as
with the other
20,
stuff, but like,
therefore we are going to have
Then
total
connect it
electron
into-
of 20. So we need to find the spaces for those 20 electrons, yeah?
Ask me your friend.
So filling
Why?
sheet
Ask
wants
the-
to
ask
be
Daryl
found
apply.
with this
No, something like.
There's no internship.
3S,
why don't apply school?
3D, 4S, 4B,
Apply school intern.
4D, 4. I'm going to stop here because I feel this is enough, yeah? So let's first fill this one answer shell. This will have,
not bad.
this can accommodate 2 electrons, and then our next
Better than not.
shell is going to be 2s, which will accommodate 2
Clean out, clean
electrons again, and then the next sequence will follow this arrow. So we are going to have 6 electron in the 2p, and then 2 electron in the 3s, and then the next sequence will follow this, yeah? 3p will accommodate 6. So let me count how many electrons we already accommodated, yeah? So 6, 8, 10,
They should ask you to do a part-time job in
18.
taking.
So we already found spaces for
Right.
18 electrons, and then we left with only 2 electrons. And then the next share is
Self-
filled with 4s. Luckily, it can accommodate maximum 2 electrons. And so now we find all the spaces. So electronic configuration for this expansion is going to be written as
When I sell, I will donate
I will
money.
just
So it's up
copy
to
this,
you.
isn't it?
I
So
won't keep.
one
I just say I
S2,
won't
Actually, you should
two
let us keep for
S2,
spare.
two P6, three S2, three
keep. You got two hands to work, right? You can buy yourself, right?
So this
Those
is
kids at the
all.
orphanage, no fucking
Yeah.
family.
And
No
Sorry,
fucking.
they
then
don't have iPad.
one
No,
thing
it's
you may want to
Yeah, but
be
no,
careful
I'm
is
not giving them
that
pencil, I'm giving them money, bro.
4S is filled
Taking other people's money.
Okay.
It's not
earlier than the
Finance
increase.
keeper.
Okay, so we
Our
will
conversation
have
is
3P and then jump to 4S instead of filling the 3D. Yeah? That's why this is important to use this sequence. Now let's try to find the space of an electronic let's find the values of this quantum state, yeah? All those 20 electrons. So we will start with 1s2. So again, I will make a kind of table. So 1s2 have a physical quantum number as 1. Alright? And then our orbital number is going to be 0 because we look at this S shell, yeah? So this is going to be 0. And then it's around the magnetic quantum number is going to be 0. And then under here we have 2 spins.
I'm 74.
Yeah? Let's move on to this 2s2. Our principal quantum number is 2. And then our the orbital angular quantum number, okay, orbital quantum number is 0 again because we look at this S. Alright? Then where the allow the magnetic number 0 and then we will have 2 spins. Let's move on to this 2p shell. So our principal number is 2 and then following this value and then now our sub-shell becomes p, so our L is 1.
You understand the
And
actual
then with this one of this orbital quantum number, there are 3 different,
part, I don't really know, I just apply for
magnetic
I don't
quantum
know which one,
numbers
I don't know
as
part 2, I never do.
minus 1,
I don't know how to start.
0.
As in your explanation, I understand.
Answer.
I understand.
Okay?
I
And
see
each
explanation.
of these magnetic quantum
Oh, this one
numbers
ah?
can
I never noticed. I
have
don't
2
know.
spins.
What is that? Quantum is not like applying formula.
And then those blank space I just copy above, yeah? 1, 1.
Oh, I didn't understand.
Now let's move on to these 3
Now
X
what
shell.
holidays?
Alright, so for the 3 X shell, our principal quantum number is 3.
No, I started in June.
And then our
Yeah, we didn't
orbital
have
quantum
time.
number is S.
Tutor.
Therefore, we consider S, therefore
do
this
tutor
must
or
be
something
0.
like this.
Yeah? And then it's a magnetic
It's random,
quantum
like
number is
some
going to
people.
0. And then
Primary school.
under here we have 2
Comes
spins.
from teacher.
Unlike,
Now let's move
When you
on
find out
to
about
this
what-
3P6.
actually, depends
Right,
on
so
if you apply through,
principal
apply
quantum
for
number
four,
is
you can
still
apply for
3, and then
apply-
our
you don't apply through
orbital
those spots.
quantum number
Yeah.
is going to be 1.
As in like, it's
Yeah?
not very
So
good.
this is
It's
1.
very
Yeah.
good.
And
I
then
don't
under
agree.
this
No,
one
same.
of this orbital quantum number, we can find the
Yeah.
3
It's like, oh,
magnetic quantum number, yeah? And
I forget, kind of forget.
minus 1, 0, 1. Yeah? And then each of these magnetic quantum number will have 2 spins, okay?
Actually, 每个 prof 讲这个很差，在那个
Alright, and then for the flex, like
Bad
I have the way copy the logo.
No,
Alright,
graph,
and then now we have the last one for X2, so I'm going to extend this table. So for this 4S2,
What is
okay,
secondary school?
4S2, our principal quantum number is
I think
4
it's
in
zero
this,
here.
so we have 4.
Second school is what?
No.
Combined size teach.
And then because we consider this S shell, therefore this orbital number is 1, 0, orbital number is 0. Then magnetic quantum number 0, and then we have 2.
Take it slow.
So now we find all the 20 electrons with quantum values, yeah? And then we don't need to worry about this maximum number of unspined electrons because we actually have all the field shells, okay?
Just need to
Sorry. chemistry, like in an hour 50.
More than that, somebody 80 though. if you're very good.
So
Actually,
this
charge
is
very cheap though.
electron
Also, charge very cheap like this. Eh, why ah?
and then we can
That's
find
very
this.
cheap what. I see a lot. I see.
One day.
I then going back to the
One day,
particular
one
question.
day, 100 plus.
Some faster check 80.
Yeah,
Like all the
question number
reference
4.
watching.
A pulse laser delivers 10 nanojoule pulse of 1 megawatt peak power.
Actually, I
If
don't
the
know how to
photons
charge.
have a wavelength of this, how many photons
Very
are
expensive.
contained in one
Very
pulse?
expensive JC.
And then if the pulse
Really also
repeats
have
at the frequency of 20 hertz, then determine the
Big
average
analog
power.
Yeah, I think maybe.
So,
200
Yeah,
dollars.
some BPA.
How do you do the big?
Yeah, I go apply BPA.
so where we now
Low bid.
consider a
Low.
pulse rate, okay?
And three
Pulse rate. So we have pulse, okay, power, HP. And then the pulse duration is given as 10 nanoseconds. And then the peak
Oh,
power
it's like NIE.
I don't have
is
to
given as 1 megawatt.
Uni also need NIE.
Then how many photons are confined in one
I don't
pulse?
have any again.
So how many pulses do we have here? So we will use this equation. Yeah? So energy of the photon is
Got another degree,
calculated
2
as
degree.
total number of the photons times
One.
h c over lambda. Alright? And then we know that this energy is related to the power as power times its pulse duration. Let me say this is the power. Okay? So operation time. So power.
This my song.
And then wavelength is given as 694.3 nanometers. Peak power given as 1 megawatt, and the duration is also given. Therefore, you can solve this for the total number of photons. Yeah. So let's solve this. Now, in the second question, it states that this pulse repeats at a frequency of 20 hertz. So in other words, along this time axis, this pulse appears repeatedly at every 20 hertz. So I can set this repetition, okay? 20 hertz, therefore 1 over 20 seconds. Okay, every 1 over 20 seconds, we have this pulse, yeah?
One Thailand.
Then we want to find this average power. So our average power is going to be calculated in this way. So when this power is only can only be measured, okay, when it's on. So when the pulse is on, there is 1 megawatt, no 1 megawatt. But when the pulse is off, there is no power at all. And then at this when it hits this period, then we are going to have another pulse. So in order to find this average power for the including this on time and the off time, what we are going to do is we are going to chop off this pulse power. Okay, and then this pulse power will be used to fill this off time. This is going to be used to fill this off time. Then we can define this average power. So this height is our average power. Yeah. Then from this you can actually come up with one equation. Peak power times its pulse duration, yeah, is equals the average power times its temporal frequency, which is 1 over 20. Because this is used to fill this off time. Yeah? Therefore, you can solve this for the average power, where all the rest are already given.
Formula sheet 有吗？这 formula sheet 有吗？
没有。
What's going on?
The average power.
So, for the number of photons, so we first calculate the first energy, and then first energy is related to this total photon number,
P
and
laser
then we
you got
can
P
find the number of
Your teacher-
哦，你
photons,
在讲 number
and then the average power is going to be calculated at 0.21.
，B 你在说 energy formula 不是咩？
Now, let me see if I miss any positive impression. No, yeah. So well, we cover all the positive impression, but I want to show you one more question that is not included in the tutorial, but I think this is a useful question to understand the X-ray, right? So I'm going to read the question. The electrons are accelerated from the rest state by the electric potential difference, and then bombarded on a metal to generate K alpha, K beta line, and then this energy state of K and M are all given. Then with this, what is the minimum value of the accelerating potential difference? Okay, then we'll commit this K alpha and K beta line. So, what's the first requirement to have K lines? So in order to have these K lines, what do you have? What's the first requirement? The first requirement is to create vacancy in the K shell, isn't it? You must have the vacancy in the K shell, then the electrons in the upper area will be excited to this vacancy which will generate these K lines. Yeah? So the very first requirement is to kick out the electron in the K shell, from the K shell. Okay? So the energy of the K shell, is 70 kiloelectronvolts. So we need at least this much of the energy to kick out the electron from the K shell. So the required accelerating potential is related to, this potential, okay, potential is related to the potential energy, which is going to be potential times this time. This must be 70 electron volts, which is the energy of in the K shell. Then, of course, this Q is going to be your electric charge, electron charge, and then you can solve this for this potential, right? Then, what's the wavelength of the K alpha and the K beta line? Well, K alpha is accounting for energy from energy from, so this K alpha, okay, accounts for the energy difference between EL minus EK. EL and the EK, they are all given in the question, okay, and then this difference is going to now related to the H over here. And then the wavelength for this K beta line, so you can also find this as this, yeah? So K beta line is related to KEL minus EM. Those energies given in the question, therefore this is related to this lambda for the beta line. Okay, so you solve this for the wavelength. So I think that's all for these tutorials. Then as I announced in the
when 那个 energy
As I
下来
announced
的
in
时候，
the this course slide,
但是
I'm
没有
going
做
to
完，其实
review
其实那个够噻，其实只是去搞一个那个 transform 那个 K 消。
我看到你说，我没看完，你要回去。
So this is your assignment. So let us first start with test number 1. Yeah. So the light intensity threshold or light vision device is 4.10 to minus 11 per meter square at the wavelength of 500 nanometers. If the light with this intensity and the 500 nanometer wavelength enters on eye, and then the foot here is open to its maximum diameter 8.5 millimeters, then how many photons per second enter the
I
eye.
think Shen is the dog.
So this kind of questions has been well introduced in our first
He's a dog.
tutorial,
That
yeah, in
is
the
friends with them.
quantum
He's
of
like,
physics.
he
So,
like give me the
Who is that?
triggers lah.
so well,
Is
intensity
it the very
is
tall?
given
Yeah,
as
very
4 times
Yeah,
10 to
it's
minus
really
11
I think he about as
watts
well
per meter square.
This
And
Amanda.
then diameter of the pupil is given as
He quite nice,
8.5 millimeter.
To me,
And then,
That's why you look at me.
well, when it
I work
comes to
at-
this, the quantum physics, then we know that our energy
One punch up.
is related to
Right.
number of photon times h times f.
What's the you and him fighting over Amanda?
Okay, and then this becomes
The
an
fuck?
You, Daryl, his theory.
g over lambda.
Huh?
And then you know that
What?
this energy is actually
Useless.
power times operation time, isn't it?
Feel like talking to him.
And then our power is
Destroy.
intensity times area.
We should destroy him.
Okay,
You
times.
sure you?
Therefore, our photon per second or per time is going to be I
You go for me?
area,
I
okay,
later ask her.
divided by hc times the wavelength, yeah? And then this numerical value is 5.7 times 10 to 3 per second. Okay, so you can solve this. Now let's go back to this second question.
Show me.
So in our second question, we have the UV beam with a wavelength of 200 nanometer, which is incident on the matter. If the stopping potential of the photoelectron is 2.8 volts, determine the work function and the color frequency of the matter. So when we
T-by create some fucking fancy
consider the
stuff.
photoelectric effect, then we will always start with this mass equation. Yeah? So our mass equation is K max equals HM minus pi, which is our work function, equals the stopping potential times is the charge. Yeah? So in the question, wavelength is given, so I'm going to convert this in terms of the wavelength, which is 0 lambda minus 1 times Q. So wavelength is given, and then the stopping potential is given. Therefore, you are going to use this to calculate your work function. Yeah? So your work function is calculated as 3.4 electron volt. Alright? Now, because this work function is now determined, you can calculate this cutoff frequency. So at the cutoff, this becomes 0, yeah, at the cutoff. In other words, Hg over lambda c minus pi is equal to 0. So this was just determined, and then you can solve this for this lambda c. Okay, sorry, here we want to find the total frequency. So this is going to convert it as Fc minus pi equals 0. So your total frequency is going to be pi over h, which is 8.2 times 10 to 14. Okay. Now, let's look at question number 3. A photon with a wavelength of 110 nanometer is incident on a ground state hydrogen atom. Determine the photon energy in the electron volt. Can the photon be absorbed by this hydrogen atom? And then explain the region, what will be the state of the hydrogen atom after the interaction. So hydrogen, so the hydrogen is exposed to this wavelength, yeah? So then let's see what will happen. Wavelength 110 nanometer. Okay? And then this wavelength 11 electron volt. So this is 11 electron volt, okay? And then, because we are considering the hydrogen atom, so I can draw some diagram for this hydrogen atom actually. So our ground state have the principal constant number over 1, and then we will have 2 and 3, and then of course we can expand this more. So the hydrogen atom is at the ground state initially, therefore under this irradiation, this ground state can be excited to the upper state. Yeah? In order to calculate this, we are going to use this equation. Yeah? The energy for the hydrogen atom. So En equals minus 13.6 electron volt over n squared. Okay. So this is the hydrogen atom's energy. Then, wherefore the first transition, all right. So our delta E1 to 2 is going to be E2 minus E1, and then if you calculate this becomes 10.2 electron volt. Okay.
Isn't it always initial minus final?
No, it's final was initial.
It's not
And
final
then
initial.
our next excitation will happen between 1 and 3.
No,
Okay.
to be honest,
It
doesn't matter.
happens, so then this becomes
Doesn't
E3 minus
doesn't matter.
E1, and then
Magnitude, yeah.
this is found as 12.1.
Doesn't matter.
So this transition requires 12.1. And then our incident photon has 11 electron volts, so our incident photon will make excitation like this. Okay? Up to 11 electrons. So as you can see here, this much of energy does not match to either of the required transition energy. Therefore, this photon won't make any excitation of the hydrogen. So we will conclude that there is no excitation. So the hydrogen atom after the interaction will remain in the ground state. Right?
Okay.
Now, some of you actually use the Bartos series.
The sign.
So you're wrong.
For instance,
We put
this
n equal to.
equation, yeah? So,
Oh, really?
after
It was 2.4 complete.
Actually, you stay at the ground state.
I'll
After
1
interaction.
over 2 there minus
What's the
4.
what's the 2.4?
I mean, I thought you go to the closest one, you know.
For the Bartos series, yeah? And then you, in this case, the
Okay,
n
whatever,
start
I
with
guess.
3, 4, 5, and then well, all the way to the final.
The blind leading the blind.
If you want to use this equation,
together.
alright, then the shortest wavelength you can get from this equation is going to
I thought you would just go to the
is going to be found with the infinity of this n number.
Should I myself?
Then your
来语法。
wavelength is going to be somewhere about 350 now.
Because I also copy, I also know to
Okay, so this Bartos series can only express or only applicable to the wavelength longer than 350 nanometers. Our wavelength is 110 nanometers, so we are not going to
That
use
makes sense though,
computation.
yeah,
Yeah.
was, yeah.
So yeah, but and also please calculate this properly. Yeah, so 350 is my approximation. Okay, it might be shorter than this or longer than this, but it's not going to be a big difference. But well, this is my estimation to just to show you that this is
And not
only
just
for
that.
the big wave.
拜四，
明天
明天内。
So then,
is tomorrow.
I'm going to
Yeah.
move on
Good
to
for you,
the
Sam.
next
Good for you to
question.
say.
I really need your help. I
I'm not
really
ready.
tell you. I not kidding.
很难读。
Question number
我
4.
在做 like 很 like from 7
The
点
distance
到10点多，
between
因为
atoms in a
Why would it
crystal
go?
is 0.2
Finally,
nanometers.
right.
The crystal is being
Let's go.
studied in
Whatever is
an
ever
electron
is
diffraction experiment. Determine the speed of electrons, so the electron to Broglie wavelength is 0.28 nanometers. If the electrons are replaced with neutrons
I don't know,
determine
but then
the
just
speed of the neutron
feeling.
in order that the neutron Debroglie wavelength is 2.28 nanometer, which is the same. Yeah.
他这样做啊，在
So
Gone. Don't do very hard.
they know how to do the second question. They don't know how to do the second question.
the Christopher quantum lattice constant
I feel that
is
you
given
have to
as
correct.
0.28 nanometer, and then the Debroglie wavelength of the electron also given as 0.28 nanometer. So this wavelength is a good selection. Yeah, this is a good choice, because this is comparable to this the lattice constant. So this electron can actually see
It's
the
like
electrons
calculation of
under
anything.
atomic
This is my
structure.
time.
Yeah, so this is good wavelength.
Students have to do.
Then with that, we want to calculate the speed of this electron. So well, through these Debroglie wavelengths, the momentum and then wave are connected. Yeah? So we can say that this momentum, which is m times v, is going to be h over lambda. So next of the electron, you can find the question in the list of constants. Therefore, you can solve this for this v. Alright, and then this v is V is 2.6 times 10 to 6 meter per second. Yes? And then now this electron is replaced by neutron. So momentum for the neutron is going to be m over the neutron times v equals h over lambda. And then for the neutron, the Debroglie wavelength is the same. We want to use 0.28. So we can just solve this for this speed, and then because the mass of this neutron is also given in the constant, this constant, also in the question. Therefore, our speed for the neutron is 1.4 times 10 to the 3. Alright? So